Okay, hello, good afternoon, class. Today we'll be talking about carbonyl chemistry. Here is the outline of discussion for our topic this afternoon. First, we'll be discussing or we'll be investigating the nature of carbonyl compounds or the carbonyl functional group. Next, we'll be talking about how carbonyl compounds are prepared, which includes redox reactions and hydration tautomerism of alkynes. Third, we'll be talking about reactions of carbonyl molecules or carbonyl containing molecules such as nucleophilic addition, electrophilic alpha substitution, and nucleophilic addition by carbonyl compound to another, which includes the following subtopics on aldol addition reaction, cross aldol reaction, aldol condensation reaction, and finally double aldol reaction. And in additional to that, we also have Glycine addition reaction. Furthermore, we would also be talking about nucleophilic conjugate addition or the beta addition. And the last reaction is about miscellaneous reactions of carbonyl containing molecules. These miscellaneous reactions include Wittig and Wolff-Kishner reaction. Okay, first and foremost, the carbonyl functional group, this one, has a carbon double bond oxygen, and the oxygen of the carbonyl group can be a Lewis base and a Bronson base because it can donate its electron pair and it could also accept hydrogen ions. The carbon of the carbonyl functional group acts as a Lewis acid or an electrophile, and the alpha carbon here can act as a Bronson acid because it is quite acidic due to the inductive effect of the carbonyl functional group. The carbonyl functional group can undergo a process called enolization. So from a carbonyl, it could be converted to an enol, and this enolization reaction is a rearrangement reaction that naturally occurs to enol and ketone. So this interchangeability wherein an enol is spontaneously converted to ketone is what we call tautomerism or keto-enol tautomerism. So based on the enolization of the carbonyl molecule, the alpha carbon can act as a Lewis base or nucleophile. So it could act as a strong nucleophile. Okay, here are the ways to prepare carbonyl molecules. The first one is oxidation of alcohol. In this case, we have to use a weaker oxidizing agent and not potassium permanganate, because if we use potassium permanganate to primary alcohols, we would form carboxylic acids. But in this context, a weaker oxidizing agent such as PCC and DMP, or pyridinium chlorochromate and DMP is Des-Martin periodinane, can convert primary alcohols to aldehydes. Secondly, secondary alcohols can be converted to ketones by using PCC, DMP, or potassium permanganate. Next one is the reduction of carboxylic acid and their derivatives through the reducing agent called DIBA, diisobutyl aluminum hydride. So using DIBA to carboxylic acid and carboxylic acid derivatives can convert them to aldehydes. So these are the ways to prepare aldehydes and ketones. You could also prepare aldehydes and ketones through hydration and tautomerism of alkynes. So we have the Bronson acid catalyzed hydration, which would form an enol. Here is our enol, and this would tautomerize to ketone. Also, hydroboration of alkynes can form an enol. It's following a anti-Markovnikov addition, and it could undergo tautomerism to form ketone, to form an aldehyde. One more thing is that oxidative cleavage of alkenes can also form aldehydes and ketones. Okay, so here are the reactions of carbonyl molecules. Due to the fact that the carbonyl carbon here is an electrophile, it's a weak electrophile, then it means that it can undergo nucleophilic addition. So a nucleophile will react to this position here in the carbonyl carbon. There are two types of carbonyl addition, a nucleophilic addition to the carbonyl group, as shown in the general mechanism. So we have a carbonyl molecule, carbonyl containing molecule that is being attacked by a strong nucleophile to form an alkoxide intermediate. This alkoxide intermediate will act as a base, a bronzed base, and will abstract a hydrogen from a hydrogen ion source to form the alcohol product. So any strong nucleophile will do in this case, such as carbon ion nucleophile from Grignard reagent. Secondly, weak nucleophiles can still interact with this electrophilic carbon of the carbonyl group if the carbonyl group is activated. So we have two types of activators. One is bronzed acid activator, the other one is Lewis acid activator. So the bronzed acid or the Lewis acid activator can form a fully positive carbonyl group. So this electrophilic carbon can undergo a resonance structure which make it fully positive, something like this. So now it becomes a fully positive carbon and now a strong electrophile. Now being a strong electrophile, a weak nucleophile, this one, can attack to it. Now the weak nucleophile attaches to it in this case and a bronzed base from the background will obstruct the hydrogen of the nucleophile to form the final product, which is an alcohol product. Examples of these reactions are shown in the following figure. So in the first case, we have addition of a strong nucleophile. It could be addition of Grignard reagent. So the carbon ion from Grignard reagent will add to the electrophilic carbonyl group, electrophilic carbonyl carbon, and forms the alcohol product afterwards. The second scenario is the addition of a weak nucleophile, such as hemiacetal formation. So in this hemiacetal formation, the first step is the activation of the carbonyl group to make the partially positive carbonyl group into a fully positive carbonyl group. So now it becomes a strong electrophile. Now, the weak nucleophile can attack to it, forming this tetrahedral intermediate. And this tetrahedral intermediate can be reacted with a bronzed base to form the final product, which is a hemiacetal. Okay, so a special nucleophilic addition reaction is the protection of carbonyl group. Okay, suppose we have this example. We have a carbonyl group containing an aldehyde and an alcohol, a secondary alcohol for that matter. But we would like to oxidize this molecule to form this product, okay, from reactant 1 to product 2, which means that we only needed to oxidize the hydroxyl group and not the carbonyl group. So how do we do that? In order to selectively oxidize the hydroxyl group, which is the yellow one, we need to use a protecting agent. So one way of protecting the carbonyl group is by converting it to an acetal. So the protecting agent used here is ethylene glycol or ethane 1,2-diol, which converts this ethylene glycol or ethane 1,2-diol are sources of weak nucleophile. It's a source of weak nucleophile and converts the carbonyl group to an acetal. So the first step in this protection of alcohol or protection of carbonyl group is the activation of the carbonyl group, and that is bronzed acid activation for that matter. Now this bronzed acid activation will convert the partially positive carbon to fully positive carbon. Now it becomes a strong electrophile, and due to being a strong electrophile, a weak nucleophile can now react to it. Now the weak nucleophile will attach to it bearing a positive 1 formal charge. Now in order to relieve the positive 1 formal charge, a bronzed base will abstract its extra hydrogen, abstract its acidic hydrogen, and form a hemiacetal. So this product is a hemiacetal, and the same process can occur. So the hydroxyl group, this group for that matter, shall be protonated with a strong acid to form water. So the water molecule here is formed, and take note that water molecule is a very good leaving group. So this water molecule will leave through this lone pair pushing it away, and now converting the carbon a strong electrophile. So now it becomes a strong electrophile. This carbon is now a strong electrophile, which shall be attacked by your weak nucleophile in an intramolecular manner. So this one is what they call an intramolecular nucleophilic addition. So this is what happened there. We have we have a weak nucleophile attacking a strong electrophile in an intramolecular manner. Intramolecular addition, meaning it's within the molecule. Now, the Bronsted base will obstruct this hydrogen to relieve the positive one formal charge in the hydrogen. So this one is a Bronsted base. It's a conjugate base of sulfuric acid to form the acetal product. So the acetal product is immune to oxidation. So it cannot be oxidized by your oxidizing agent. Now, what happens is that if we summarize the step from reactant 1, we form this protected product, reactant 1 protected. Now we have an acetal moiety here. So this one is an acetal. And we have a hydroxyl group here. Now we would like to add an oxidizing agent, which is potassium permanganate. This potassium permanganate will oxidize selectively the hydroxyl group and not the acetal. So we form the oxidized protected product 2, and this protected product 2 will be subjected to acidic hydrolytic condition in the presence of water and sulfuric acid. The dip protection step is formed, or the dip protecting step is conducted. So the acetal is converted to terminal carbonyl group afterwards. So that is how we do protection of carbonyl group to selectively oxidize one of the other functional groups and prevent the oxidation of terminal carbonyl groups. Okay, some other reactions of carbonyl molecules or carbonyl containing molecules is the electrophilic alpha substitution. So take note that the alpha carbon, in this case, the alpha carbon is being substituted by another electrophile. So from the name itself, it's electrophilic alpha substitution. So we have an alpha carbon here, this one, substituted with another electrophile. So that is the essence of this type of reaction. In this case, it's important to know that the alpha carbon will act as a strong nucleophile through enolization. So it's a very important concept to consider. Okay, there are two types of enolization. The first one is the acid catalyzed enolization, and the other one is the basic catalyzed enolization. So remember that the alpha carbon, this one, is slightly acidic for the reason that the carbonyl group will exert a negative inductive effect to it, which results to a lessened electron cloud density to that of the alpha hydrogen, making it slightly acidic. However, despite it being acidic, it's not that easily attacked by any other base. So we have to, in acid catalyzed enolization, we have to activate the carbonyl group first. We have to activate the carbonyl group first. This one is the activation step. And this activated product will form a fully positive carbonyl group or carbonyl carbon. So this fully positive carbonyl carbon will lessen the pKa value of the alpha hydrogen. So in reactant 1, the pKa of this hydrogen is 20, but after activation, reactant 1 activated, the pKa of the alpha hydrogen, which is shaded in green, now becomes 0.8. So it becomes very acidic to the point that the conjugate base of your acid can easily obstruct it. So take note that this process is reversible. The conjugate base of the acid can obstruct the alpha hydrogen this time. So now, after obstructing the alpha hydrogen, which is shaded in green, the product called enol is now produced. So we have product 1, which is called enol. So we have reactant 1 converted to activated reactant 1 converted to enol product. So remember that the alpha carbon of enol is a strong nucleophile. So being a strong nucleophile, it can interact with any electrophile. Okay, so that's how an electrophilic alpha substitution can occur. Okay, later I will show that particular reaction. The second way to enolize carbonyl containing compounds is through base-catalyzed enolization. So in base-catalyzed enolization, a strong base that can obstruct the alpha carbon is being used. So this strong base, okay, this process is reversible depending on the type of base that is being used. Okay, it could be reversible, it could be not reversible. Okay, a strong base can obstruct the alpha hydrogen, this is our alpha hydrogen, and this obstruction will lead to the formation of a carbon ion. This one, we have carbon ion or an enolate. So the carbon ion can further assume another resonance form which is called an enolate. But in both forms, the alpha carbon is the one that is nucleophilic. So we have a nucleophilic carbon here which reacts to another electrophile. Now what happens in electrophilic alpha substitution? So in electrophilic alpha substitution, the first step is always enolization. So remember, it's always the first step. It could either be acidic enolization or basic enolization, or enolization in acidic or basic conditions. If the enolization is in acidic conditions, the product is an enol. If enolization is in basic conditions, the product is enolate. And remember that enol and enolate have a nucleophilic alpha carbon. So this alpha carbon acts as a nucleophile. So this is our nucleophile, a strong nucleophile for that matter. And being a strong nucleophile, it can attack to an electrophile. After attacking the electrophile, what happens afterwards is an alpha substituted product. So this is our product. It's alpha substituted because one of its substituents has been removed or replaced by another one. Okay, examples of electrophilic alpha substitution reaction is we have bromination of aldehydes and ketones. In bromination of aldehydes and ketones, the first step is always enolization, remember? So in this context, we use a basic enolization to form an enolate. So this is our intermediate. It's called an enolate. And the alpha carbon, this carbon, serves as our nucleophile, a strong nucleophile which reacts to an electrophile. So this is our electrophile, and that is being reacted with our enolate. Okay, so this is our product. What happens if sodium hydroxide and bromine are added in excess? So if the base and the electrophile is added in excess, it means that the reaction will proceed subsequently to substitute all the hydrogens in the alpha carbon. So it now becomes a hexabrominated carbonyl compound. Okay, another type of alpha substitution reaction provided here is alkylation of aldehydes and ketones. So we have our ketone here for that matter, ketone number 1, which is reacted by sodium hydroxide, and this hydroxide base will obstruct the alpha hydrogen. So this hydrogen is obstructed to form an enolate structure. So this is our enolate, which is a nucleophile. So the enolate nucleophile will attack an alkyl halide. So our alkyl halide will act as an electrophile to form the alkylated product. We have substituted the alpha position with an alkyl group through this type of reaction. Okay, a special alpha substitution reaction is what we call Helmholtz-Zielinski reaction. So Helmholtz-Zielinski reaction is an alpha substitution reaction that occurs in the context of carboxylic acids. Remember that enolization of carboxylic acids is difficult for the reason that the carboxyl hydrogen will act as, okay, the carboxyl hydrogen, this one, will act as a Bronsted acid that is more acidic than our alpha hydrogen. So this is our alpha hydrogen, and it is more acidic than it's less acidic than the carboxyl hydrogen. So therefore we have carboxyl hydrogen being more acidic than alpha hydrogen. So in this case, if you perform enolization in both acidic and basic conditions, what is reacted by the conjugate base or the base or the Bronsted base is the carboxyl hydrogen, the blue one, and not the alpha hydrogen. So this is reacted and not this one. So it's very difficult to perform enolization in this manner. So Hell-Vollard-Zielinski reaction is a special type of alpha substitution reaction which forms enolization but through a different means. So the first step in this reaction is the conversion of carboxylic acid to acid bromide. So it's a conversion to carboxylic acid derivative. So we have a carboxylic acid here converted to an acid bromide or carboxylic acid derivative. So this is done through the process of addition of phosphorus tribromide, and this addition of phosphorus tribromide will convert it to carboxylic acid derivative. In particular, we have acid bromide here. So now the acid bromide can undergo tautomerism reaction. This carboxylic acid derivative will undergo tautomerism reaction, which converts the alpha carbon into a strong nucleophile. So this one is a strong nucleophile this time, and this strong nucleophile will attack a weak electrophile, and the weak electrophile will now be attached to our alpha carbon, successfully substituting the alpha carbon. So we have a successful alpha substitution reaction here in the context of Hell-Vollard-Zielinski reaction through conversion of carboxylic acid to carboxylic acid derivatives. So the last step in this reaction is addition of water to hydrolyze the acid bromide back to carboxylic acid. Okay, another type of reaction of aldehydes and ketones is what we call the nucleophilic addition by the alpha carbon, the alpha carbon of a carbonyl containing compound to another carbonyl containing compound. So this type of reaction is a named reaction. It is named as aldol addition reaction. In this case, it is a self-aldol reaction because it only reacts with itself. Suppose we have a carbonyl containing molecule 1, we have 2 moles of it, and this molecule 1 is enolized through addition of base or acid. We have 1 mole of base or an acid, and we have 2 moles of our starting material. And this reaction will result to the formation of a product called beta hydroxyaldehyde or beta hydroxyketone. So this product will give us an idea why it is called aldol. Because remember, hydroxy is from alcohol, and aldehyde, we have ald. So I believe that aldol can be derived from the product called beta hydroxyaldehyde. So aldehyde, it's ald, and hydroxy is alcohol, so all. So that's aldol reaction. But what actually happened here? So we have our starting material. 1 mole of it is enolized through either acidic or basic enolization. So when we have acidic enolization, we form an enol here. And remember that enol is the alpha carbon of enol is a strong nucleophile. And under basic enolization, we form an enolate here. The alpha carbon of enolate is also a strong nucleophile. Originally, we've had 2 moles, but 1 mole of it is converted to enol. And enol or enolate, the other mole of our starting material will act as an electrophile. So it is reacted by our enol or enolate to form the product, which is a beta hydroxyaldehyde. Once again, we have a ketone or aldehyde starting material undergoing enolization to form enolate or enol. The enolate or enol will attack the remaining molecules of aldehyde or ketone starting material to form the product, which is a beta hydroxyaldehyde or beta hydroxyketone. Okay, so that is the essence of aldol reaction. Okay, so let me show you an example here. We have acetaldehyde. The alpha hydrogen of acetaldehyde is being obstructed by a Bronsted base to form an enolate. Okay, we have 2 moles of acetaldehyde and 1 mole of sodium hydroxide added. We have 1 mole of enolate, and enolate is a nucleophile. Okay, this enolate will react with the remaining 1 mole of unenolized acetaldehyde. So this remaining 1 mole will be acting as an electrophile and reacted with 1 mole of the enolate, okay, to form this product here. This one is an alkoxide product. The alkoxide product will abstract the hydrogen from water to form the alpha hydroxy aldehyde product. Okay, in acidic conditions, so the first one is basic condition, the second one is acidic condition. Okay, in acidic condition, first we need to activate the carbonyl group through addition of sulfuric acid. Now this activation will result to increased acidity of alpha hydrogen, so this alpha hydrogen will now be very acidic to the point that the conjugate base will act as a bronzed acid to abstract this alpha hydrogen. So what is formed after abstraction of the alpha hydrogen is 1 mole of an enol, which acts as our nucleophile, and the remaining unenolized acetaldehyde, this one, will serve as an electrophile to be reacted by your nucleophile. So what is formed afterwards is an alkoxide product, but this alkoxide product will be converted to this alkoxide product will be converted to an alpha hydroxy aldehyde product after this oxygen alkoxide group abstract this hydrogen of your carbonyl group to form this product. We have an alpha hydroxy aldehyde product afterwards. Okay, the next reaction here is what they call the cross-aldol reaction. So the previous reaction is self-aldol reaction, but what we have here is a cross-aldol reaction. So in cross-aldol reaction, we have a different source of nucleophile and a different source of electrophile. So the source of nucleophile is what we call an aldol donor, so the one that enolizes or the one that forms an enolate or enol. That's what we call the aldol donor, and the aldol acceptor is our electrophile. So we have an electrophile here, and we have our nucleophile source. Okay, so this cross-aldol reaction will yield the same product as before, alpha hydroxy aldehyde and ketone. Okay, the general mechanism for cross-aldol reaction is the same with that of the self-aldol reaction. The only difference is our source of electrophile. The first step of aldol reaction is always enolization. It's either through acidic enolization or basic enolization to form an enol in acidic condition or enolate in the basic condition. So this enol and enolate can act as a nucleophile to react with our electrophile, which is what we call an aldol acceptor. So enol and enolate is an aldol donor, and this one is our aldol acceptor. The product is an alkoxide intermediate, but through the reaction with an hydrogen source or hydrogen ion source, the final product is an alpha hydroxy aldehyde or ketone. An example provided here is we have reaction of cyclohexanone and benzaldehyde. So in these reactions, we have our aldol donor. Okay, this one can undergo enolization, and we also have an aldol acceptor. Okay, so in this reaction, it is using basic conditions, so it's base-catalyzed enolization. We have our base abstracting the alpha hydrogen first to form an enolate intermediate, and this enolate will act as a strong nucleophile and react with our weak electrophile to form an alkoxide intermediate, and this alkoxide intermediate will abstract the hydrogen of water to form the final product, which is an alpha hydroxy ketone. The third type of aldol reaction is what we call the aldol condensation reaction. Basically, it is an aldol reaction plus E1CB elimination. So suppose we have the same aldol donor and aldol acceptor. It could be for self-aldol or cross-aldol. It could occur for both. So in those scenario, we add under acidic or basic conditions, and in the presence of heat, an aldol reaction can occur, but subsequent dehydration reaction through E1CB elimination can also occur if the reaction media is heated. So what happens here is that the first step is, suppose we have a basic condition, enolization. Bronsted base will abstract the alpha hydrogen to form an enolate, and this enolate will react to an electrophile. The enolate is our aldol donor, electrophile is the aldol acceptor, and this will produce an alkoxide intermediate which will abstract a hydrogen from a hydrogen ion source to yield the alpha hydroxyketone product. Okay. Remember that the alpha hydroxyketone still has an enolizable hydrogen. So this enolizable hydrogen will be further reacted with our base, our Bronson base, to form this carbon ion, which can have a resonance structure to an enolate. Okay, this carbon ion or enolate resonance structure can undergo an E1CB elimination. So this type of movement of electrons, this one, 2, and 3, is what we call an E1CB elimination. So when we say E1CB, it's what we call conjugate base unimolecular conjugate base elimination. Unimolecular conjugate base elimination. Okay, so what is the conjugate base here? The conjugate base is the carbon ion or the enolate. Okay, and one thing is that remember that hydroxyl group carbon-oxygen bond is not polarizable. It's not polarizable. Generally, it is not polarizable except in this scenario. So in this scenario, it can be broken down because of E1CB elimination. So it's one of the rarest scenario that hydroxyl group will leave as hydroxide. Hydroxide, being a bad leaving group, would still leave because this movement of electrons, the carbon ion is a stronger base naman, and this one is a stronger base, and this one is a weaker base. Okay, so the product is a weaker base, so it's still acceptable, even though it's not the carbon between carbon the bond between carbon and hydroxyl group is not polarizable. And finally, we have this product here. This product is what we call an enone. Okay, so why is it called an enone? It's called an enone because it has an ene. This one is an ene, and this one is an one. So ene is from alkene, and one is from ketone. The product is an enone. Okay, so an example provided here is we have 2 moles of acetone here, the presence of sodium hydroxide and heat. The product is an enone. Okay, so what happens here is that the hydroxide will abstract this alpha hydrogen to form an enolate. This is our enolate nucleophile, and this enolate nucleophile will attack the other molecule of acetone to form an alkoxide intermediate, and this we have water here formed. This alkoxide will abstract the hydrogen from water to form an alpha hydroxy ketone. And now this alpha hydroxy ketone still has hydroxyl alpha hydrogen here. This can undergo further enolization to form an enolate, and this enolate group will undergo an E1CB elimination. So this E1CB elimination will remove this hydroxide to form the product, which is okay. So the product is this alkene. Okay, so this is what happens in aldol condensation reaction. The next thing is we also have what we call double aldol reaction. So how is double aldol reaction done? It is done through having 1 mole of aldol donor and 2 moles of aldol acceptor. So this double aldol reaction will have 2 nucleophilic sites. We have carbons 1 and 3, and these 2 nucleophilic sites will react with your electrophile or your aldol acceptor. So we have basic conditions here. The first one is this one, a formation of an enolate reacting with 1 mole of our aldol acceptor. benzaldehyde or benzene carbaldehyde, forming a alkoxide intermediate. This alkoxide intermediate will abstract the hydrogen of water to form an aldol product. Okay, this one is an aldol product, or alpha hydroxy ketone product, or alpha hydroxyaldehyde product. Furthermore, this hydrogen will be abstracted with hydroxide to form an to form an enolate, and this enolate will react to another aldol acceptor to form this alkoxide product, and this alkoxide product will abstract the hydrogen from water, and finally form this double aldol product. Okay, so we have a double aldol product formed after this reaction. So this is the reaction mechanism for double aldol reaction. Okay, so now we also have Glycine reaction. So instead of having an aldehyde or ketone aldol acceptor, we have an ester aldol acceptor here, or our electrophile is an ester. So here is the general mechanism for this reaction. Okay, we have, suppose we have basic condition, and in this basic condition, we form an enolate. This enolate will react with an ester. So this is our nucleophile. And it will react with our aldol acceptor, which is an ester. And this is what they call nucleophilic acyl substitution to ester. So remember that ester and carboxylic acid and derivatives can undergo nucleophilic acyl substitution. So what happens here is we have nucleophilic acyl substitution forming a tetrahedral intermediate. So what we have here is, okay, so this alkoxide tetrahedral transition state or tetrahedral intermediate. Okay, in this tetrahedral intermediate, it's the time to decide which of the following will leave and which of the following will stay. So which bond is more polarizable and which bond is not polarizable. So suppose we have a carbon-carbon bond, this one. We also have a carbon-carbon bond, this one. And finally, we have a carbon-oxygen bond, this one. So which bond shall be broken by your movement of this lone pair? So the most polarizable bond in this case is carbon. We have carbon-carbon, carbon-carbon, and carbon-oxygen bond. Okay, the carbon-oxygen bond is the most polarizable, so that is why it is the one that is ejected by this transition state. Okay, so now the product is a diketone molecule. So this is what we call diketone. It has two internal carbonyl groups. So the following is a summary of aldol reactions. The first one is we have discussed about self-aldol reaction. In self-aldol reaction, our aldol donor and aldol acceptor are the same. So basically, you have 2 moles of it. In cross-aldol reaction, we have a different aldol donor and a different aldol acceptor. So we have a different aldol donor and different aldol acceptor. In aldol condensation reaction, we can either have same or different aldol donor and acceptor, but remember that we use heat here to induce E1CB elimination. The fourth one is what we call double aldol reaction, in which 2 moles of aldol acceptor is added, and aldol donor has two nucleophilic sites, so it can undergo two enolization 2 times. So it means that we have to add 2 moles of base as well. And the last one is Glycine reaction. Our aldol donor is an aldehyde or ketone. Our aldol acceptor is an ester. So basically it is aldol reaction plus nucleophilic acyl substitution. E1CB is aldol reaction plus aldol condensation is aldol reaction plus E1CB elimination. Okay, so that is how we interpret the aldol reactions that I have introduced to you. Okay, now let's go to a special type of aldol reaction. It is what we call reductive aldol reaction, and it's what we call Aldoltischenko reaction. So in Aldoltischenko reaction, we have an aldol donor here reacted with a very strong base called LDA. LDA is what we call lithium diisopropyl lithium diisopropylamide, and this is the structure of LDA. So when LDA abstracts an alpha hydrogen, that reaction is complete, or that reaction is not reversible. So that reaction proceeds completely. So that's how strong this base is. Aldol-Tischenko reaction has two steps. One is, actually it has three steps. Aldol-Tischenko reaction has three steps. The first one is enolization, basic enolization through the use of LDA. So you form an enolate product. This one is our enolate product. And the second one is preparation of our aldol acceptor. The aldol acceptor is prepared through the use of a Lewis acid activation. Okay, this Lewis acid activation will produce a strongly electrophilic alpha carbon, which is reacted by another molecule of aldehyde or ketone. So this molecule will act as a nucleophile and attack this electrophilic carbon to form this transition state. Okay, so this transition state 1 will have a resonance structure. This transition state 1A and transition state 1B are both resonance forms. Okay, so these two transition states are the final form of our aldol acceptor. Now, the third step of Aldol-Tischenko reaction is the reaction of aldol donor and aldol acceptor. Okay, so these two are reacting in the last step of Aldol-Tischenko reaction. So what happens here is that our aldol donor and our aldol acceptor reacts. Our aldol donor and our aldol acceptor reacts to form this product. Okay, so our product is this one and an aldol donor reacting to it. Okay, so this is our product, but what happens here is that this bond, remember that this bond from our Lewis acid is like this. It's a borderline ionic bond. So what happens here is that this lone pair will be pushed into this sigma bond and breaking up this hydrogen, a carbon hydrogen bond to form a hydride. So this hydride will attack this carbon to form this type of product. So the product form is an alkoxide. So this hydrogen from that, okay, so let's color this red. This red hydrogen from our aldol acceptor attacks the carbonyl group to form an alkoxide. Okay, so this product is formed afterwards, and this alkoxide intermediate will remove a hydrogen from the background, from a hydrogen ion source, to finally produce our final product, which is a reduced aldol product. Okay, so the product is not an aldehyde or ketone but an alcohol because of reduction. So that's why Aldol-Tischenko reaction is what we call reductive aldol reaction, because this group has been reduced to alcohol. Okay, so that is the end of our topic for aldol reaction.